哦，好。
所以你们如果不想抄的话，就是我们有 PA，它会上传啊，你们就只记得可能就是
附题。
听就好。然后呢，就是我们一会儿应该会上传到 YouTube 上，那 video 已经有。那 YouTube 上面有一个功能，它是 CC Caption， 它下面会有打字啊。所以如果你们就是英文上面如果是没太听懂的话，有这兴趣的话，就是可以去YouTube 上面自己再看一下，不需要看全部，只是看那些地方。还有呢，就是大家现在有书了吗？
有。
有。是吧？是第3版吗？
那本没有找到，我找到大本，小本的找不到。
什么叫大本？
所以不是有2本吗？
哦，
我找到 system 那个没有，是 electrochemical system 没有找到，另外一个有。
Electrochemical system 那种。
那个我没有找到。
那就先看notes吧，好吧？
现在要看吗？现在要拿。
不是现在用看，就是我是说，就是如果课程上有什么不了解的话，你可以看。就是我书跟讲课跟那个书是大致上是一致的。就是现在想问一下，有哪个学生是硕一？有硕一的学生吗？有大4的学生吗？全都是大2的是吧？有上次没来过的学生吗？就你俩是吧？好 ，OK， so we'll get started, okay? So this is, so last time we started talking about just like the general introductions, okay? The first couple of lectures is going to be the introduction of basic concepts, okay? So last time we started talking about like the two original electrochemical cells, okay? The Daniell cells and the Volta files, okay? And both of them are form of like a battery, okay? They can be used for power. So we stopped talking. We stopped at the definitions. Okay? So we talked about what the electrode is, the electrolyte is, and what consists the basic components for electrochemical system. Okay? So typically, start with the drawing. So the key features for electrochemical system. Okay? EC, this stands for electrochemical. Okay? System. Okay? The key features for electrochemical system is that it has 2 electrodes. Okay? Okay? And which transport electron by external conductor. Okay? And separated by electrolyte. Okay? So for this electrochemical systems to function, okay, it has to complete the circuit. Okay? Electron is passed from the anode to the cathode while this metallic conductor. Okay? And then the current, okay, must flow, okay, from is different. Okay. The charge carrier is in the electrolyte is the ionic species. Okay. And the ionic species can be different for different electrolytes. Okay. Okay, the difference, okay, between electrochemical reaction, and so we have electrochemical system, okay, and then we have for these electrochemical system reactions, okay, is different than a typical redox reaction. Okay. So we have a redox reaction. Okay. Electrochemical reaction is versus the redox reactions. It has a couple of differences. Okay. The main difference is that the electrochemical reaction, the reduction and the oxidation occurs at different places. Okay. So, whereas for redox reactions, this is a chemical reaction. Okay. The reduction and oxidation occurs at the same place. Okay. The difference, okay, between this is difference short and it's short for difference is that the reduction and oxidation for electrochemical reactions, that occurs at different places. Or okay. Okay. So, in another word, i.e., okay, and two acids. Okay, so this is one of the main differences. Okay, this is split up into a half cell. Okay, the oxidation and the reductions are separate. Okay. The second difference between electrochemical reactions and typical redox reaction is that the electrochemical reactions, okay, is always heterogeneous. Okay. What do I mean by heterogeneous? This is another way of saying that it's a surface reaction. Okay. So the electrochemical reaction is always a surface reaction. Okay. So the rate of this electrochemical reaction is tied to the surface area. So one of the research that is very important for battery, okay, for synthesis of electrode is how to increase the specific surface area. Okay? And typically that is done by making the electrode porous. Okay? You can increase the specific surface area of the electrode. Okay? So you have an electrode, okay? If it is a flat piece of metal, okay, the surface area is just simply the length times width times 2. Okay? or if it's one-sided, it's length times width, right? But if you have a porous electrode, okay, you would have like a if this thing is porous, okay, then that specific surface areas are large. Okay? So this is the two primary difference. Okay? So okay. So these are the characteristics. Okay. So characteristics okay, for electrochemical reactions. Okay. So even though that electrochemical reactions they occur at different places, okay? The reactions at these two places are tied together. Okay? What I mean is that the rate of reactions, okay? Rate of reactions, and two electrodes form coupled. Okay, or coupled. Okay. So whatever happens here is related, is going to have an effect to what happens here. Okay. The electron generated here, it must go somewhere. Okay? Instantaneously, they must go somewhere. And so whatever electron is generated here at this half cell must eventually and instantaneously come over here. Okay? So these two, even though they happen at different half cell, their reaction rate is coupled. Okay? In that way, it's the same as the redox reaction. There's no difference. Okay? The reaction rate is coupled. Okay? And they're coupled through by two principles. Okay? They must obey the conservation of charge. Okay? Or current. Okay? What I mean by that, the charge that's generated here by the electrochemical reactions at the anode, okay, must be conserved. So the current that's being generated over here must be conserved here. Okay? And then what I mean by that is, even though there's going to be some waste heat, okay, loss of efficiency, okay, through over potential loss or whatever, but the conservation charge must be maintained, okay. Second, okay, the electron neutrality. This must hold. Okay. What I mean by this, okay. So in the electrolyte, electron neutrality must hold, meaning that whatever ionic species is present in the electrolyte, okay, the sum of the positive charge must equal to the sum of the negative charge species. So the charge must be added to zero, okay? So this must hold. C9 zero. Okay, in the electrolyte. Okay. So the current scenario over here flow through the metallic conductor to over here at the interface, okay, between the electrode and the electrolyte, okay. The charge, okay, change from current, okay, to an ion, okay. So and this change, okay, this change from, so this is metallic conductor, okay. This is the medium, okay. This is the medium, and the charge carrier. In the metallic conductor is the electron, right? Whereas in the electrolyte, okay, the charge carrier becomes the ions. Make sense? So through coupling, okay, the reactions, okay, of the two half cells, okay, and holding true the conservation of charge. Charge and current is the same, okay, they're the same, okay, and holding true electron neutrality, okay. This circuit, okay, this is how the circuit is maintained, okay. If for whatever reason this is not true, then the circuit will stop and no current will flow, okay. So, so we talked about the previously, okay, we talked about previously the reactions, okay, and at the electrochemical reactions, okay. So for instance, last time we so if this is the zinc, okay, then this is the silver, okay. So we have the electrochemical reaction, zinc plus 2OH minus. Okay, so this is at the anode, okay, and the cathode is silver, okay. So this goes to 3 times plus zinc oxide. Okay, and then at the cathode we have silver oxide plus H2O plus electron. Okay, goes to silver plus OH minus. Okay. And to make the electron balance, you put 2 in front. Okay. So for these reactions, okay, for these half-cell reactions, okay, there's a specific current, okay, that's associated with it, okay? And Faraday's law, okay, is used, okay, the law that relates the rate of reaction to the current, okay, okay, is the Faraday's law. Okay. So Faraday's law states total mass produced, okay, is proportionate to amount of charge. Charge, I'm going to use the simple Q, okay, times equivalent weight, okay, of species. Okay? So, total mass, MI, okay, is equal to Q times MI times NO. Okay? This is Faraday's constant. Okay, which is equal to 96487 coulombs. Okay, per equivalent. Okay, 96487 coulombs. Okay, then is the number of electron transferred. And Q is the charge. Okay. And MI is the molecular weight. Okay. So Q here. So Q is equal to SI by dt. Okay. So the SI is the stoichiometric coefficient. Okay. I is the current. And T is the time, okay, in seconds. Okay. So as this reaction proceeds, okay, the zinc is gonna turn into zinc oxide, okay, and then this silver oxide is gonna react with water, turn into zinc. Okay? It's gonna become bright. Okay. Okay. So this Faraday's law, okay, relates how much current, okay, you can get. Okay. So this is another form. Okay. So MI is equal to minus SI I T. And then, okay. So this is another form of Faraday's law. It's more common, okay?
个符号？
啊，
为什么有个符号？
这个负号是是一个 convention， 就是人家习惯写这个符号。
那为什么前面那个没有？
啊，
为什么那个没有？
这个啊，
嗯。
哦，你可以多加一个。好吧。对，这一个有符号跟没有符号是一个 convention， 有些时候有些书里面是有，有些书里面是没有。就是这跟年代有关。
可是这个 mass 不是应该是正的吗？所以是那边有东西是负的吗？
这个符号跟那个 mass 没有什么关系。这个符号是跟它的它的热力学有关，就是它是他会跟你讲说这个东西是倾向于就是往哪个方向？然后方向，OK，这个 sign，OK，this is a convention，OK，what I'm going to tell you is might sound confusing to you, but to electrical engineers it's not, okay. So the convention is this is a convention, okay. Current, okay. I, okay, is defined as the flow of positive charge. Okay. Flow of positive charge. Okay. Current is defined as flow of positive charge. Okay. Okay. And electron, okay, flow is the opposite. So this is what I'm saying, okay, this is convention, okay? So it's weird, right? But intuitively we know that electron will float, right? Electron will float, they have a tendency. Okay, it has something to do with thermodynamics, okay? So the electron feels better to be feels more on silk, on silk. Okay, so if you connect the two, the electron will spontaneous flow from zinc to silk. Okay, so electron is flowing this way. Okay, but current, you write current, okay, is flowing the other way. So current is the flow of positive charge. I don't know why, but it's okay. So another important definition is the concept of current density. Current density. So this is current. Okay, this is current density. This is capital Y. This is little I. Okay. Don't ask me why. And this is charge is Q. Okay. So we're gonna keep this consistent. Okay. So make that a small cube. Okay. Okay. And this is molecular weight. concept, a lot of people may get confused, okay? Current density is defined as the flux of charge, okay? So is the flow of charge per unit area. Okay. So for the electrochemical system, okay, the performance of the electrochemical system, all electrochemical systems are heterogeneous systems, okay? So the current density it's a very key parameter, okay? So the performance of the electrochemical system, the rate, okay? For instance, how fast you can charge your electric Tesla, okay, or your Gogoro, okay, is tied to the rate in which you can charge the lithium-ion battery, and that's a performance parameter that's tied to the current density. Okay, how fast you can charge your Tesla and your Gogoro is it's a direct function of the current density parameter for the battery. Okay, for that electrochemical system, which is mostly a function of the electrolyte. Okay, it's inorganic electrolyte, which has a very, very low conductivity. Okay, so the performance of the electrochemical system is more proportionate to the current density, the small I, okay, than the total current, okay? And the total current I is simply I times A, okay? Okay, so another important concept is depolarization. Polarization. Okay. So what is depolarization? Is defined as departure of potential. Okay. From equilibrium. Condition. Current is constant. Okay, so when you connect the anode to the cathode, okay, theoretically you're going to get X number of volts. For instance, if you have a zinc and a silver, okay, let's say you have like perhaps theoretically like 1 point something volts, but you only get 90% of that. The loss is due to polarization. Okay? And that polarization can be is related to this over potential. Okay? So this is the magnitude of potential drop. By resistance to the passage of currents. Okay. So polarization is it's a sum of the over potential. Okay. So you're gonna have like different things that cause different. This over potential has there's different over potentials and they add up to the polarization. Okay. We'll go into that later on.
不用说我的眼睛，
啊
没有错。
就是polarization 是就是比如说你有100% voltage theoretical 对吧 ？polarization 就是会造成你就只有90%，对吧？那10%就是它的 loss 对吧？是 polarization。然后 polarization 是由不同的 over potential 造成的。这只是名词，名词。待会儿我们把这些东西就是列出来以后你就明白了，好吧？Okay, so these are some of the examples. Okay, some of the key concepts. Okay, we talked about the key concepts. Okay, examples of volatiles and Daniel cells. Talked about the specific components. Okay, and we talked about some of the key principles earlier. So that ties the current produced to the max. Okay. Okay. And then we talked about some of the important concepts and vocabulary. Okay. So.这本书我订了，可能要2-3个月我才到。不好意思。
抱歉，那个等下下课了，就灯关掉，门关上，因为晚上还有课。
哦。
他只是反锁，抱歉。
那我要做什么？
没有，就是灯都关掉，然后门带上，不要锁。
好，
谢谢，谢谢，抱歉。
Okay, so that's the introduction of the basic concepts. Now we're going to go into some of the we're going to go into the fundamentals. Okay, so the fundamentals are thermodynamics. Kinetics and transport. Okay? All very chemical engineering, right? Right? Okay. So let's start with the thermodynamics. Okay. So thermodynamics and potential. Okay. So, in a boulder pile, okay, this is a boulder pile, okay? If the current is complete, okay, the silver oxide, okay, this tarnished silver, okay, this is actual silver oxide. Okay, so this tarnished silver will disappear to form silver. Okay, and then this zinc will dissolve. Okay, and turn to zinc oxide. Okay. So what caused the spontaneous formation of silver and spontaneous dissolution of zinc is the thermodynamics. Okay, and the short answer is the electrochemical potential of this couple. Okay, so what caused the reaction in a volcano? Electrodes are connected. Okay. Specifically, is the delta G, okay, which is the Gibbs. This is, you guys know what the delta G is. Delta G, the Gibbs free energy, okay, the electrochemical potential of the product. Okay. Right. Minus the electrochemical potential of the reaction. Okay. So again, this is the stoichiometric coefficient. That's not. It's the same as before. Okay. And this is the electrochemical potential. Stoichiometric coefficient. And then this is the Gibbs free energy. Okay. So the energy of reaction, okay, for this reaction, okay, is given by the change of Gibbs free energy, okay, for each half cell reactions. Okay. So again, I'll write that. We have zinc plus 2OH minus goes to 2E minus plus zinc oxide plus H2O. Okay? And then this is the anode. Now we have the cathode. We have silver oxide plus H2O plus 2H2O plus 2E goes to 2 silver plus 2OH minus. Okay? So if this, if delta G, okay, if the Gibbs free energy for this reaction is delta G, okay, is negative. Okay. looking at this equation, okay? So looking at this anode reaction, okay? Zinc plus 2OH minus is going to go into 2E minus plus zinc oxide plus H2O. Okay, if you do the summation for the stoichiometric coefficient and the electrochemical potential. The electrochemical potential, there's a book. I don't have it here. But in one of the books, right, you can look it up in the table. Okay? And from there you can calculate the delta G for this reaction. Okay? If that delta G is negative, okay, it means that this reaction will occur spontaneously and in the left-hand direction. Okay? What does that mean if this delta G is negative? Looking at this reaction, this equation, okay? Looking at this equation, okay? What does it mean if delta G is negative? If you have this minus that, this is negative, right? Then that means, which one's bigger? Here or here? The first term is bigger than the second term, or the second term is bigger than the first term? What? So the second term is bigger, right? So if the second term is bigger than the first term, then delta G will be negative, right? Okay, so it means that this is more positive. Right? Right? Okay. So the right hand side is more positive than the left hand side. Okay? And so the right electrode is more it's a more positive electrode. Okay? Okay? So you can look at this as, so this is on the half cell level, okay? On the cell level, okay? Delta G is equal to G of the product minus G of the reactant. Right? Yeah? Okay, now I want to introduce another concept. Okay? So suppose we have in this multiply, okay? We route this thing through a potential stack. Okay, a high impedance potential high impedance potential stack. Okay, so a high impedance potential stack is something that can it's a device that can apply a potential. Okay, you can through a. Okay, so if this current is routed to a high impedance potential step, okay, to adjust the potential in such a way that no current is flowing between this these two electrodes, okay. So if you apply a very high potential to this potential step, so such that no current flows, okay, then the potential, okay, then the potential, okay, when no current is flowing, okay, it's called the equilibrium. Or open circuit potential. It's either the equilibrium open circuit potential. Okay? And this has this open circuit potential or equilibrium potential is simple big U, okay? And this is in joule per coulomb. Joule per coulomb or volts. Okay? Okay? So this big U is the open circuit potential or the equilibrium potential. So if there is no current flow, if you apply the potential high enough such that no current flow, okay, then the potential that you detect through the potential step, okay, is U. That is the equilibrium or open circuit potential. Okay? And this is a very important parameter, okay, that identifies the pairing of these two. This is a very key parameter for this pairing of these electrodes. Okay? And this U, okay? This U, this big U, okay? This equilibrium potential is related to the Gibbs energy, okay? By the following, okay? So this delta G, okay? Delta G is equal to minus work electrode. So this is the work. Make it smaller. This is the work per unit charge. Okay, required to move charge from one electrode to another. Okay? So this is the work that's required to move per charge, okay? To move one charge from one electrode to the other. Okay? So this is related to delta G by the following, okay? And work this work is equal to NFU. Okay? So N is the number of electrons, okay? F is the Faraday's constant, and U is the big U, okay? The equilibrium potential. Okay? So, we can relate delta G now to this. Okay, so delta G now is equal to, delta G is equal to minus NF. Right?
可以让中文讲一次。
什么？
先从 U 开始，然后 U 是什么
什么？
？U 是什么？
U 是equilibrium open circuit potential， 就是这个东西等于是断的时候，它的 potential 就是 U， 懂吧 ？When this is open circuit， 就是它的 circuit 是断的时候，就是你把这个东西，如果你有把 high impedance potential stack 对吧？你把它那个 potential 调到最高的时候。这电流就断了，意思就是说这个东西是这样子，对吧？然后你测量它 potential 的时候，那个 potential 就是这个 U， 好吧？然后呢，这个 U， 我们想要知道这个 U 跟这个 G 有什么关系？好吧？首先我们先开始这个 delta G 是跟这个工作有关的。This work to remove one unit charge from one electrode to the other。你接受这个吗？
那段什么意思？
啊？
那段什么意思？
什么东西？
那个
这个是吧？
没有那个 work 的那个。
Work per unit charge required to move one charge from one electrode to another. This is the electrode, okay? This is the work that's required to move one charge from this electrode to this electrode. This is the unit of energy, right? This is the work that's required to move one charge to the other. It's simply that. Energy and energy. Okay? Simple, right? 你懂吗？这只是一个，这都是能量，这也是能量，对吧？你只是把这个能量定义为这个，对吧？然后呢，这个 work per unit charge required to move one charge from one electrode to another， 这个是它的 definition， 对吧？你有了这两个东西了以后，你就知道怎么样把 U 对等于这 delta G 了，懂了吗？
high impedance 那个 impedance 怎么拼
？IMPEDANCE， 好吧 ，OK， 不好意思啊，不写好一点。现在几点？哦，还是。we'll finish up. So, so now we have delta G is equal to minus NFU. Good? Yeah? So now we have a way to relate the change in Gibbs free energy to the equilibrium potential, or the open circuit potential. Okay, both these are energy. Okay? So this U, okay, this U is a function of chemical species, the concentration, and the temperature. Okay? So this delta G, okay, this delta G gives the Gibbs free energy. Of reaction. Oh, Gibbs energy of reaction. Gibbs energy of reaction. At equilibrium. When no current is gone. Okay? So now the question is, okay, starting from delta G, okay? How can we, okay, how can we use this information, okay, to determine U cell?这个 U 跟 U cell 是不一样的，是吧？所以 U cell 是整个 cell， 是吧？这个 U 是跟那个金属有关，好吧？So first, okay, first we write. So first we write delta G, okay, is equal to delta G naught plus RT ln gamma I SR. So this is the activity coefficient, just PCI, okay? And then this is the stoichiometric coefficient again. Okay, so this is the activity coefficient. Okay. And this is the Gibbs, the changing Gibbs energy for reaction at standard condition. Okay? So if you combine it with this reaction, with this equation over here, okay? We just said minus NFU on the left hand side, right? So we move this minus NFU to the left hand side, we get minus NFU, which is equal to delta G naught plus RT plus, RT multiply. Okay? This is multiply all this. Okay? So everything here is a product. Okay? Pi. Gamma I SI. Okay? Okay? So, oh, I'm sorry. So delta G is equal to minus NFU, then delta G naught is equal to minus NFU naught. Okay? Okay. So if you divide this minus NF throughout here, then you get U is equal to U naught minus RT NF ln pi. Okay. So this is the standard cell potential for a full cell at 25 degrees C. Okay? 什么？这个 pi 是 multiply， 就是这里面所有东西都要 multiply， 这跟这个 sum 是一个意思，这 sum 要加，是吧？这个是 multiply， 对，乘，所以这是一个符号，计算符号，
所以它乘
这里面东西全都要乘。
I 跟 S。
对，但是这个有不同的 i， 所以这里面东西是 gamma 1 s1 乘以 gamma 2 s2 乘以 gamma 3 s， 懂了吧？好 ，so this becomes that, right? Okay. So we have 2.3. No. So log, we have log of x is equal to ln x divided by 2.303, right? Remember this? Right? So I'm just gonna change that. Okay. So ln x is equal to 2.303 times log of x. Right? Okay. So we can write that as u is equal to u naught minus 2.303 RT over n log of pi gamma pi epsilon. Okay? So this is the Nernst equation. Right? Okay. So if we this is one form of Nernst equation, okay? Another form is this is Nernst equation as well, okay? So from here to here, okay? So if we assume ideal solution, okay? If you assume ideal solution, then this activity coefficient is going to be equal to 1. Okay? So gamma I is equal to 1. Okay? And then we break them apart. Okay, to product in terms of product and reactants. Okay? Then we'll get U is equal to U naught minus RT N down N pi N I SI, this is right, plus RT N down N pi N I SI. This is left. This is another form of integration. Okay, this is another form of integration. Okay, which relate the equilibrium potential. Okay, equilibrium potential to the concentration of the reactant. This is molality. Okay, MI, this is molality. Molality. Okay, this relates the equilibrium potential to the molality. This is the product. This is the reactant. Whatever's on the right is the product. Whatever on the left is the reactant. Okay. We'll just stop right here.有问题吗？
下次会带题目吗？
啊？
你会带题目吗？
什么叫题目？
就是你会讲一些，你会用这些公式，然后讲一些题目，然后告诉我们怎么做。
我们现在是在推东西，在先介绍是吧？另外一本书里面有很多很好的这种 examples， 我会跟你们讲说要做什么，好吧？
好。你会讲，已经就，我怕我写不出来。
那个轩，这可以等到周一吗？这可以等到周一。